Before I start with this topic, so this will be actually a continuation of my last talk. So for those of you who weren't here on Sunday, I think it was, I'm a little confused, so I hope you can follow. Before I start with this general talk, I was asked a lot what I'm actually doing on gravitational wave detectors. So theory, data analysis, instrumentation, so I give you just some ideas what my group is currently working on. And give you just some pictures really, really fast. So for example, we're working on strain measurements. This is actually a PhD student, Lars, which was not on the last slide. So it's just involved in more mechanical engineering stuff. So for example, we develop our own small accelerometers to measure the deformation of airplanes, actually. So the plan is to have a huge sensor network with small accelerometers or strain sensors. So we are also looking at other technologies which work completely wireless. You don't need a power, so they run with battery. And we have a wireless link to a telecommunication system where the data can then be analyzed with a rate of 100 Hertz. We have very low bit error rates and so on. And the goal is actually very similar to your problems. We want to have the strain, or in the end, even the stress of an airplane construction process. So if they bring the huge things together, we need to care about stress such that nothing is breaking. So we try to get the information from displacement measurements in 3 axes down to the stress inside the material. And we also don't know the material exactly. This is a secret. So this is one of the projects that I'm working on with Lars. And where I'm actually coming from is space-based missions, the laser interferometer space antenna, I already talked about that. And I'm interested in very precise measurements. So here 1 picometer per square root Hertz at low frequencies, so below 1 Hertz. This is what I mean by low frequencies. And this is for what I developed the optical metrology system to read out test masses in satellites, or I constructed the setups on Earth like you can see here. And I'm also looking into other interferometer techniques which provide these sensitivities but are less complex, smaller, lighter, everything which is maybe advantages for satellite missions. So here you can see I, for example, designed a single prism which does the same as this full optical bench and achieved actually similar precision. Here's just a small test mass in the middle where we tested the performance of these small single component optical sensors on Earth. I do a lot of simulations, straylight simulations. I need to tackle fiber noise, laser frequency noise, all technical noise sources, which you might also see later in my talk. So this is actually where I'm coming from. I think I can now start and continue my talk from Sunday, dealing with ground and ground-based gravitational wave detectors using distributed sensors. So I'm developing with this team sensors which are sensitive at low frequencies, high precision, I hope, so on the picometer scale. And this is the team at the University of Hamburg. That's me. This is my PhD student Reinhard and a master student Julian, who just started. And these two are Jan Harms and Francesca, both in Italy. No, she was in Italy. And they are the experts for Newtonian noise cancellation systems and simulations on this regard. I think this was one of the last slides that I had on Sunday. How do we go from advanced LIGO or Virgo, the second generation of detectors, to the next generation of detectors on ground? This was a measurement. This is the next generation design sensitivity of future gravitational wave detectors. We need to be better by 1 order of magnitude over the full frequency range. And at low frequencies, we actually want to have 6 orders of magnitude. So we need improved seismic isolation, as I told you. And a new noise source will come up, which was called Newtonian noise. And this is something which was modeled here by Jan Harms from surface waves, and we will look now into this noise source a little bit more in detail. So we need to tackle this Newtonian noise. What is Newtonian noise? If you have a seismic wave, it will produce mass density changes in Earth, and this will produce, if it's a changing acceleration or a changing mass, produce changing acceleration, produce changing force. And this changing force will influence the acceleration of your test mass. It's a gravitational force, so it will be bypassed by any isolation system we put on. So seismic isolation systems don't help. We don't have something like a Newtonian noise sensor yet. So gravitational wave detectors are the best Newtonian noise sensors that we have. We could just build another one, but yeah. So the idea was, how do we get rid of this kind of Newtonian noise, which will actually limit us here at low frequencies. And the idea was, from Jan Harms, test mass acceleration depends or is directly correlated to seismic displacement or changes in seismic displacement, so the gradient. You need to know the density and volume of your ground. You also need to know the composition of your seismic wave, and you also need somehow to know where it is, roughly, in dependency on your with respect to your test mass. But from this formula, it should be clear if we measure the seismic field, we can somehow predict the acceleration and then make use of it for the data acquisition system. So the idea was, or I could maybe just conclude, Newtonian noise is a direct consequence from seismic waves. We have a problem with body waves because surface waves are getting suppressed. If you go, for example, underground is planned for the next generation of gravitational wave detectors, but body waves are not suppressed, or the Newtonian noise from body waves is not suppressed in gravitational wave detectors. So we need some cancellation systems, and the idea was to measure the seismic field based on this equation and then do the post-processing for the data chain. And this is how it looks like. So we need to measure the seismic field. We have seismometers, and then we have some algorithms, some Wiener filter or surrogate Wiener filters, which reconstruct or which filter our data such that we can get a reconstruction of our seismic field as best as possible, 12 degrees of freedom. To do so, we need a lot of seismic sensors. We need an array. I think I don't need to tell you this. And then we can use this formula, put it in here for the seismic displacement measurement and calculate the expected acceleration. And then we can see whether we can actually subtract it in our science data from the Einstein telescope, for which we will optimize this full system, which is why I also put it at the beginning of this plot. The simulations that has been done so far from Francesca actually, and what I'm now working also on, are based on analytical equations, like the equations that you have seen before, this acceleration here. It's put it here again, and this is now the equation, I think, for body waves with 2 times the contribution of p waves with respect to the s waves, for example. So this is just the base model that we had. We also have a lot of other assumptions. So the Earth is homogeneous, isotropic. We have this special ratio, as I just told you. The test mass is perfectly centered in an underground spherical cavity. So a lot of optimal assumptions that go into these analytical Newtonian noise cancellation simulations. And what we do in the end is we build our Wiener filter, like it is depicted here, based on cross-power spectral densities. So we use, for example, the cross-power spectral densities between the individual seismometers in this huge sensor network. Then you have the cross-power spectral densities between the seismometer and the test mass, which gives you an idea of how the coupling works. And then, of course, we need also the gravitational coupling, which is here. This is the Newtonian noise. This is the spectral density of the Newtonian noise. So in the end, we just compare something that we assume, so this Newtonian noise, this acceleration, with something that we measure. So we put it, it's all based on this equation in principle. And then we calculate the residuals based on this equation here, and you see that it depends on the seismic frequency. So imagine that you have now one array of seismometers, and you put everything in here, you calculate all the cross-spectral densities, then it will just be optimized, for example, for one frequency. And if you look at other frequencies, it will be a little bit worse. There's an best Newtonian noise cancellation system that you can find. This is if you have, for example, n equal seismometers, assuming that they are all perfect, they have all the same signal-to-noise ratio, and they produce all exact copies of Newtonian noise. So this is really the best case. Then the coherence or the correlation, the cross-spectral densities between Newtonian noise and seismic noise and the sensors is actually 1. So this is just perfect. So in the best case, it just scales with the number of seismometers and their noise, their signal-to-noise ratio squared. And this is something what we do as a check in our simulations. We assume a relatively easy seismic field and then test whether this equation is actually true. And here you can see some results from Francesca for Newtonian noise cancellation using body waves in an underground detector. I don't remember the depths. And she used a seismometer arrays to measure body waves. She actually figured out that this is more demanding than the Newtonian noise cancellation system for Rayleigh waves, so surface waves, because of several reasons. Because we don't know exactly what the contribution between P and S waves is, and this really influences the simulations. And she also found out, you can also see it here, that there's actually no unique optimum. So you find actually several local minima. So here, for example, this is one optimization algorithm, and here she just used another optimization algorithm in Python. Here you can see it for 1 axis seismometer and here 3 axes. And you can see here she did it for, I don't remember the number of seismometers, but she did the one, I think, 100 times. And here you can just see all the results. And this one here is the residuals, so the equation that I just showed you before. It should be as low as possible. For example, a factor of 0.1 would give you noise cancellation suppression of a factor of 10. 0.1 is 10. And you can see here that it doesn't matter. We have 1 axis seismometers, we have 3 axis seismometers, we use different optimization algorithms. Yeah, we get different positions for the seismometer around the test mass, which is here in the middle, but they all reach similar residuals. So we cannot go much better. And we also see that actually a 3-axis seismometer is not really helpful because the most sensitive direction is in horizontal direction. So the interferometer has test masses, and the most sensitive direction is of course along the test masses in X direction. So more seismometers or more degrees of freedom are maybe not as helpful as we actually thought. Yeah, so these are the first results that she got. There's also a paper about it if you want to know more about this. And then she did also like testing how many seismometers do I need for a certain suppression factor. So as I told, so this one here, 1 is no suppression at all. If you go down, so you calculate here the residuals, this is 0.1, this gives you a suppression factor of 10. So you can reduce the noise in the detector by a factor of 10, which would be sufficient. This was, for example, achieved for about 14 seismometers if you use the 3-axis seismometer. So you can gain a little bit if you use these 3 axes, and I think most of the seismometers actually has 3 axes. So 14 test masses, 14 seismometers for 1 single test mass, 1 single frequency of a seismic wave. And here's just the optimal case. So this is really the sensor noise, what we would have in the end. If the seismic field would be perfect, all seismometers are perfect and so on. And you see here in the end for really high seismometers, the slope is actually the same. So in the end, if we have a lot of seismometers, it actually follows this equation because we just don't get any, we just make use of the noise of the seismometers by averaging if we have more seismometers. Yes. She also investigated how sensitive this cancellation system is if you now wiggle a little bit on the position of the seismometers, and she figured out that a deviation of 0.07 times the seismic wavelength, so about 50 meters, so it depends on the wavelength of your seismic wave, but you don't need to place the sensors more accurate than a couple of 10 meters, which is already a good sign. So then you can still get suppression factors of 3, which might be actually sufficient for some of the sites which are maybe relevant for the Einstein telescope. However, so Let us assume that we need something like 20 seismometers to have a good Newtonian noise cancellation system, maybe also at other frequencies, make it a little bit more broad. Then we have 12 test masses in the Einstein telescope, which would need such a Newtonian noise cancellation system, which makes at least 240 seismometers, each in one borehole. So 240 boreholes around this 10-kilometer structure of the Einstein telescope. We need high precision seismometers with high signal-to-noise ratio, broadband, below 10 Hertz. And if we need several boreholes, or we maybe don't want to use seismometers, but fibers, which are maybe not fulfilling this requirement actually, but still, a fiber could maybe reduce the number of boreholes because you can put several ones, you just have more flexibility. But still you need individual boreholes, individual fibers, which cannot be read out with one single interrogator currently, which are on the market. And this is why I'm looking into other techniques. I think I don't need to explain you how the optical time domain or the dust system in general are working, but they also have some other limitations, especially for the Einstein telescope. So for example, the fiber length is always determined by the sampling frequency, or vice versa. For Einstein, we're looking at low frequencies, it's fine. The spatial resolution is also determined by the pulse width. This is also something that we can maybe deal with the Einstein telescope. But the main point is that we will have multiple fibers in different boreholes, so we would need multiple interrogators, which needs to be synchronized with each other. We think that the broadband performance is not good enough currently, and we have some unknown nodes where we don't have any control. We cannot look into the interrogator, it's a black box, and it's also less flexible in settings. How to improve these kind of systems, which are already really good and really a lot of engineering went there. So if you want to have a good dust system, you can, for example, use engineered fibers, which provides a better signal-to-noise ratio. But then you need an engineered interrogator to this. And this is where I'm coming in. So I was thinking about using engineered fibers, however they look like, fiber back gratings or mating sleeves which are connected to each other, or maybe even small accelerometers, like small suspended glass pieces inside a fiber, and then developing my own interrogator which has the flexibility that I would like to have. And this is a technique that I studied during my master's in Hanover actually. The interrogator is not based on a pulse, but it uses a continuous wave laser. And the trick is now to distinguish between these two different segments. For example, in an optical fiber, you're not using a pulse, but you're modulating the phase of your laser light. So you imprint a pseudo-random noise code on the electromagnetic wave. So your electromagnetic wave is, for example, a cosine. Then you imprint a pseudo-random noise code by either 0, nothing happens, or pi, so you shift your cosine by pi, which produces you an amplitude modulation by -1. So your amplitude is just going down to, just flipping the amplitude. So it looks really, really weird as a really weird signal, which means the individual back reflections here, if they don't overlap perfectly, so if they are not correlated, you can distinguish between those two. In the end, of course, you need to somehow extract the phase or the strain of the fiber. So you need to recover the original signal. And this is what will be done in the digital signal processing unit. So you need to find the right delay. So you have here your code, your timestamp, so to say, on your beam. You need to find the right delay where your target is. Then you shift, you take a copy of this, you shift it a little bit, you make the amplitude modulation gone, and then you can recover your original signal. If you have the wrong code, or maybe a wrong delay, you will just produce another amplitude modulation, so it looks like this. And then you can distinguish between these different segments and the suppression between these individual channels, for example, from mirror 1, mirror 2. If the delay is matched, you have a perfect autocorrelation, which is hopefully 1. If it's not matched, you have this background noise which depends on the length of which depends on the autocorrelation function, and this noise here depends on the length of your code, the pseudo-random noise code, the length of your signal, the correlation length. And this is the main idea of the scheme. And I did some experiments in Hanover. This was a free beam setup. As you can see here, it was set up on an optical table, no vacuum, no temperature control, just in air. This is the main advantage of this. And we had two mirrors, mirror 1, where the beam was reflected, mirror 2, where the beam was reflected, so this was just partially reflecting. And then we used a really high-speed pseudo-random noise code up to 1.25 gigahertz, which gives us a spatial resolution of 12 centimeters in air. In fiber, you have a refractive index, you can actually go a little bit closer. So this would be the optimal spatial resolution if you modulate with these high frequencies. So this is actually still the world record. Never did this again because most of the applications actually don't need this, but we were just curious how this works out. And here you can see the mirror motion. This is now given in meter per square root hertz, so we are always plotting linear spectral densities. And this is the displacement of the mirror motion, which was quite high. So you can see actually micrometer noise motion because it was an air setup, air density fluctuations, and so on. So this signal was just really, really noisy. But what we have done then, you have two different mirrors. You can just use the first mirror as a reference and subtract this signal from this signal. And all noise sources which couple up to this point will just be gone because of common mode rejection. And this gives you 3 orders of magnitude performance. And we did another measurement or another test with these data, for example, because you measure this position here of this mirror twice. You have the first reflection, which reflects directly, which can be corrected by A. And you have also the first round trip between these two mirrors, which can also be corrected by A. And then we look what is the difference between B and C. And this is here the red line, which gives us our sensing noise. So there should be no air density fluctuation, so everything should be vanished. And this gives you actually really nice performances here down to, this is 1 picometer, for example. Here we are at 100 picometer and everything at low frequencies. Here's 1 hertz, 1 millihertz. Okay, here's just a little bit noisier, but. And we also tried to get this noise a little bit more down. This was actually an effect of this really high speed that we were using. So this was a limiting factor in this line. It was a little bit more complicated, but we were able to, I think this one here is another plot. This is the line from just our previous measurements that we have seen, and we were able to get it actually down a little bit more. This is now given in phase. I'm really sorry. This is now a different unit, but I put you the number here. This is then the 20 picometer at 10 millihertz, what we achieved in this setup. We needed some clock jitter correction for this, if this is maybe important for you. Yeah, here I try to compare the measurements that we have achieved with the free beam setup with a current DAS system. And this is really not easy, because as I told you, we are always measuring in phase or meter and not in strain, so to say. And the DAS systems actually plotted in power spectrum density. I think I tried to find the best DAS system which is currently available at low frequencies, but I'm really not sure. So if you have better information than I have, I would be very happy to look also in other DAS systems. But I think, hopefully I scaled it correctly, because here the low noise from the DAS system scales actually with laser frequency noise from the laser, which was used in the system. So I think if they were limited by laser frequency noise and it just followed this line, this should be somehow correct, this comparison, but I don't know. Yeah, and the most DAS system below 10 hertz or even below 1 hertz have a lot of noise. And as you can see here, we could maybe gain one order of magnitude improvements if we use such a continuous system that I have tested in a free beam setup. Of course, this is not a fair comparison. This is a fiber, this is free beam. So here you add, of course, there's also fiber noise included, which is not included in here yet. So there's some engineering that needs to be done in the end. And if I scale this correctly, for a 10-meter baseline, you can achieve something like picostrain or 10 picostrain for these kind of systems, hopefully. As I said, again, there will be a lot of noise sources. I just put them here. What I expect from my broadband, digitally interferometer dust system. Fiber noise is the first one, but there are already experiments which are actually using digital interferometry in fibers, because it's much more easier to test this technique in fibers, because you can just curl it, make very long delays, and then you don't need this high speed frequency modulation, which is one of the main noise sources in our setup. We will have laser frequency noise, autocorrelation suppression. If you have a lot of channels in one fiber, you need to take care of this multi-channel noise, but this was investigated by our colleagues at the ANU, the Australian National Institute, where actually the technique comes from, and they investigated this. About 2,000 channels is not a problem. The noise is below 1 picometer if you want to stay there. The main disadvantage is that we need a sophisticated digital signal processing system, which might be quite fast, depends on your spatial resolution that you want to have. But I think this is something that we can actually tackle in modern times. So we shift all the optical complexity to the digital world, and it's also not like that the current interrogators don't require high-speed digital signal processing. It's actually the same. And the costs for polarization maintaining fibers, we are testing different fibers, but maybe to achieve the performance, we actually need to go to polarization maintaining, and then the costs are really, really high. Here you can see one of the measurements, also regarding this phase noise. This is from Jan Harms, was measured at the Pinion Flat Observatory. And it's again, this is a 1 strain meter versus seismometer in one borehole. So this is not a dust system, it's just a strain meter. And you can see here they measure both perfectly the microseismic peaks, but at low frequencies, the strain meter goes up, the seismometer is broadband. So this might be laser frequency noise or fiber length noise that we really need to tackle. But with digital interferometry, you can actually make a quasi-distributed system, as I just showed to you, also to a strain meter, because you can combine the individual signals in the digital processing system. I will skip laser frequency noise and just show you some potentials for the Einstein telescope. What can this new interrogator do? We can read out multiple fibers. For example, you can just curl them and have a different delay. Then you can also read out multiple fibers and just connect them to the device, because you can distinguish between individual boreholes, or you use just another PIN code, which could also help. You can, of course, also do distributed sensings if you put mirrors in the fiber, like it is already done, engineered fibers. We have only one central interrogator station, which doesn't need to be synchronized to other stations. We can do a digital strain meter configuration in the digital world. I hope we can tackle low frequency noise, also by combining different signals, like it has been demonstrated in the free beam setup. The fiber length is not longer coupled to the sampling rate or the pulse repetition, so we can actually also measure higher frequencies if this is somehow interesting. And we also want to look in whether we can use the transmitted light of a fiber and not only the reflected one. And we hope that we can also gain a little bit more signal-to-noise ratio by using a continuous wave setup, because then we can also average over longer times, measure over longer times, and hope that we can get better resolution with this. And another idea was not only to use fibers for seismic, but also for temperatures, because we could easily just connect another fiber. Why not use a temperature sensor just next to another one? Yep, and I think this is already my last slide. So this is what I was talking about. Those are the people which support me and are working on the individual projects. And yeah, after summer also a new PhD student will start working on these projects. And what we are currently doing is also within the WAVE initiative on Hamburg. This will actually be my last slide. We investigate currently the coupling of fibers to concrete. So here you can see actually a tunnel which is about 70 meters long. You have here some slits where we can actually put the fiber like this. Currently it is installed straight on in some different ways. As you can see here, this is actually a special fiber which is curled to be also sensitive to other wavelengths. And here you can see how we put it in the concrete. So this is what Julian is currently doing in his master project. And this is somehow related to the WAVE initiative, a seismic network in Hamburg, which is an initiative between the University of Hamburg, the DESI people, and myself, so Helmut Schmidt University. And this is a fiber network that we have running. We did some measurements in 2021, so you can see a lot of seismometers which were in 2021 here on the campus. And these red and blue line are the fibers. In a tunnel means blue, underground, so not tunnel, but yeah, means wet. So we have different couplings already on the campus and different seismometers, different geophones with which we can compare it. And we try to improve the research on the campus by controlling the seismic noise there and trying to localize, identify noise sources, doing structural monitoring systems, and also seismology, of course. So Celine is also here and does some correlation measurements. And yeah, we are looking always for people who are actually working on these kind of projects. I think I'm done. And if you have questions, I'm happy to answer them.